This is a classic paper review for deep learning course. The paper that I have chosen is Visualizing and Understanding Convolutional Networks by these two authors. They are from New York University. In the time that the authors wrote this paper, CNNs have started to become popular for image classification, but there was no explanation on how do they perform this job so well. So they proposed some visualization techniques to gain insight about the different layers of a neural network. Specifically, they chose AlexNet, which was the state-of-the-art neural network model at that time for image classification. Using the information they gained from visualizing different layers of AlexNet, they could build a better architecture. Despite that these models work very well, there was little understanding on how do these models classify the images so good. So this lack of knowledge limits the improvement, and if there is a problem inside the model, it is very hard to recognize and solve it. So authors try to overcome this issue and proposed a visualization technique to recognize at the level of each layer which inputs excite a specific feature map. Also, using this visualization technique, we can see how features during training and across different layers are developing. This can be used to recognize if there is a problem inside the model. The technique actually uses a deconvolutional network which has the transposes of the convolutions as the layers in order to map the activations back to the input image so that we can see which parts of the input image are important for the classification. Here are some of the attempts that other authors have made. One of the attempts is to use gradient descent in each unit to maximize the unit's activation. But the issue was that this doesn't provide any information about the unit's invariances and the patterns that do not change. Another attempt was to utilize the Hessian of the given unit, which is the second order partial derivatives. So when we calculate around a optimal response, they can be used to get insight in the invariances. One is a visualization that shows which pieces in a data set make strong activation in high-level layers. The author's approach is similar but different in a way that they didn't use pieces of the images. They performed full projection to show what patterns in each patch excite a specific feature map. This is the architecture that the authors have used to perform their visualization on. Here we can see that input images are fed into 96 convolutions and then followed by a max pooling in the first layer. The authors aim to understand how the intermediate layers work. So they used the convolutions to map the features back to the input pixel space. To inspect a specific activation, they set other activations to 0 and perform a deconvolution on the features to get the results in the image pixel space. As you can see in the figure, to do the opposite of what is done in a CNN model, in the CNN model, the layers should be reversed. So a convolution would become the transpose of the convolution, the ReLU will remain ReLU, and the max pooling will become what they call unpooling. So because the max pooling cannot be reversed exactly, the unpooling performs an approximation just to remember which patterns excited that specific activation later. The first figure here shows that in the first layer, a few of the filters dominate the others. So to overcome this issue, the authors have further renormalized the convolutions with root mean square higher than a fixed value. Also, the authors have done some data augmentation to increase the training size. So in here, we can see how how the features have evolved across different layers. They have changed from edges and corners in the first layers to actually some patterns in the last layers. The authors have shown 9 strongest activations for a feature map in the visualization. This is a way to show the different structures that respond to a specific feature map, despite different changes. This was an attempt to gain some information about the invariances. Here we can see what excites those activations. For example, in layer 4, dog faces, cyclic objects, car wheels have been excited the corresponding feature maps, despite some small changes in different images. This figure shows the evolution of the 9 strongest feature maps across all layers. For the lower layers, the patterns will be developed sooner and in smaller number of epochs, but it takes a while for the patterns in the higher layers to be developed because they are more complex. Here we can see how many epochs was necessary for the patterns to develop in different layers. We can see that at the first epoch we could have seen the edges at the first layer, but it took 64 epochs to the patterns at the fifth layer to appear. The authors have checked the model for feature invariances. The result was that the network was invariant to translation and scaling, but not to rotation in general. The visualization of the layers can be used to see the strength and the drawbacks of the architecture and then to improve it. Here, the authors have visualized the layers of the AlexNet and observed that the first and the second layer filters reveal that they are very sensitive to very high and very low frequencies, but they do not detect middle level frequencies. Another problem is that the second layer filters copy the artifacts inside the filters. In here, you can see the artifacts that are copied inside the filters. This is because in AlexNet, they have used a stride of large size. Here, the authors have tried to overcome the issues in the architecture by reducing both the filter size and the stride size. In here, we can see that how they have improved AlexNet. These are the artifacts of the second layer, and this one is the second layer of the author's model. We can see that the patterns are more clear in here. One of the important questions in image classification is that do the model recognize the location of an object correctly or not? The authors have tried to approach this question by occluding different locations in image and see how the classifier changes. For example, in here they put a gray square in different places of the image to see how does it affect the classification. The result was that the model recognizes the location of the object to some extent, because what can be seen from the visualization is that is that, for example, if the dog's face is occluded, the classifier would not be able to classify it correctly. But if a location in the background is occluded, like in here, it classifies it correctly. The authors have replicated the state-of-the-art models at that time for image classification. They have used ImageNet dataset. Then they have compared the results from those models with the result of their own model. In the last row, we can see that the model is reduced error in comparison to other models. Changes that they have made is that they have put 7x7 filters in first layer and the straight side 2 convolutions in layer 1 and layer 2, and stride of size 2 convolutions in layer 1 and layer 2. The authors have generalized the features trained by ImageNet and built the model by using the pre-trained model to do image classification on other image datasets. What they have done is that they have fixed the first 7 layers trained by the ImageNet dataset, and they've added a softmax classifier on top of that. Then they just trained the parameters of the softmax classifier on each of those datasets, and they have checked the performance. For Caltech-101 dataset, the metric that they have used to compare the pre-trained and non-pre-trained models' performance is the average accuracy of each class for a sample of that class. We can see that the accuracy of the pre-trained model is twice as of that for the non-pre-trained model. The increase in performance is more obvious for the Caltech 256 dataset. By looking at different metrics of different sample sizes, we can see the increase in performance for ImageNet pre-trained model. The performance is not much better for the experiment in PASCAL dataset. They have used a softmax with 20 probability classes on top of the pre-trained ImageNet model. We can see even a slight decrease of performance in some classes. The reason may be because some images in PASCAL datasets are multi-labeled, or that there is some background behind the object, so the features trained by ImageNet are not useful for PASCAL, or sometimes it's even confusing. Another analysis the authors have done is to see at each layer how much do the feature maps contribute in classification. For examining each layer, they removed the next layers and added a SVM or softmax on top of the layer and performed the classification. As expected, we can see that the higher the layer, the more contribution it does. In conclusion, the authors have examined the performance of different CNNs for image classification. They have presented a visualization method, and they have used it to find problems in AlexNet, and they have modified the architecture to overcome these issues. They have also trained the architecture on ImageNet dataset and showed that it has a good performance on 2 other datasets. Thank you.